We know that the kinetic molecular theory applies to ideal gases, and that ideal gases have no particle volume, they have no intermolecular forces, they move only in a straight line and with constant motion, and they're mostly empty space. But when we look at the molar volume, 1 mole at STP, which is something you've calculated, which should be 22.41 liters per mole, we can see that while most gases at STP come pretty close, not all do. Carbon dioxide is a little further off than ammonia, nitrogen, helium, or hydrogen, and chlorine is even further off. So we have real gases which don't necessarily obey the ideal gas law. That doesn't mean we can break the ideal gas law, but it does mean we have to modify it a little bit. But before we get that far, let's take a look at real gases in a little more detail. So let's take a look at real gases. Essentially, everything you need to know is on this slide, but we'll go through it. Experimentally, when the molar or the volume gets very, very small, or the pressure gets very, very large, we see that the volume is larger than what we would predict the volume to be. So we can calculate the volume with PV equals nRT, but when measured, it's actually a little higher. So we can take a look at why with these pictures up at the top. When the volume is large, the particles have a lot of room to move around, and they act as independent, tiny little particles with essentially no volume, because they're so small compared to the volume of the container. But then, for the picture on the right, when we add lots and lots of pressure, we're squishing all these particles together in a tiny little space. At this point, those particle volumes starts to matter. We have to correct for that actual particle volume when we're looking at the gas laws. And we'll see how that happens in just a little minute, in a minute or two. The other non-ideal behavior is intermolecular forces. At very, very low temperatures, or again at high concentrations, but it's easier to describe at low temperatures first. At very, very low temperatures, the kinetic energy is very low, and so these molecules or particles are not moving very quickly. So while for a normal gas, an ideal gas, each of these 4 particles would be bouncing off the wall, causing pressure, for a real gas that has intermolecular forces, when these molecules or particles are moving so slowly that they have time to run into each other and stay attracted to each other, it's almost like there's a single particle running into the wall. Less collisions, less pressure. With high concentrations, you would also think that that would mean that there would be more particles colliding into the wall. But with high concentrations, there's also a higher likelihood of particles having interactions and intermolecular attractions, so the scenario on the right is more likely. So, summarizing this, at very, very low volumes or very, very high pressure, we have to account for the fact that particles have real volume. At very, very low temperatures or very, very high concentrations, we have to account for the fact that particles interact and have intermolecular forces. Therefore, they act as though fewer particles are colliding against the wall. So what's happened is that we have the real gas van der Waals equation. Fortunately for you, the AP test people took this equation off the AP test, so you're not going to have to actually do calculations with it. You can see, though, that it's very similar to the ideal gas law. We didn't throw out the ideal gas law, we modified it. Because if we can provide an instance where the law is not valid, we need to make modifications. So it turns out that the observed pressure is lower than the ideal pressure, and it's lower by this amount, N the number of moles over V, so that's molarity squared times an experimentally determined constant. And the volume of the container measures too high, you have to subtract off the number of moles times an experimental constant. So the van der Waals equation is just like the ideal gas law, except it has to make corrections for the fact that it's a real gas. Measured pressure is too low. Measured volume is too high. And it happens when the gas is closer to a liquid. So as the molecules are forced closer and closer together or have more and more intermolecular attractions. And we're going to talk about those intermolecular attractions in a great detail over the next couple of weeks. Now let's take a look at a couple of molecules and try to decide which would behave less like an ideal gas. So in this first instance, we're comparing ethane and methylpropane, and one of them is going to be less ideal because of the volume component. The larger the molecules, the more the impact as the container gets smaller and smaller or as the pressure gets greater and greater. So we can choose the larger molecule as having a larger deviation from ideal behavior. We can do the same thing with the next pair. So give those a try. Okay, sulfur dioxide is the one I chose because it is a larger molecule. So if we're going to correct for volume, the larger the molecule, the more real and less ideal. So let's go back for a second to the first graph we took a look at. You can see here helium, really small. Hydrogen, really small. Nitrogen's a little bigger, and so is ammonia, but chlorine, each chlorine atom is a pretty large atom, having all those electrons, and Cl2 is going to be a much larger molecule than helium or hydrogen. So it makes sense that this one is less ideal. Now let's take a look and see what happens in terms of intermolecular forces. We said that the larger the intermolecular forces, the larger the deviation from ideal behavior. Because when there's a lot of intermolecular forces, 4 or 5 particles could act like a single particle. So let's take a look at these. I have water and methane. Well, we haven't really talked a lot about intermolecular forces yet, and we are going to spend a huge amount of time talking about them. But one of the things that you should remember from biology and from an earlier chemistry class is hydrogen bonding. It's a fairly strong intermolecular force. And hydrogen bonding, which we're going to talk about in much more detail soon, happens between a molecule that has an OH or an NH or an FH and another nearby molecule with an O or an N or an F. So if we take a look at this first pair, we have water that has hydrogen bonding and methane that does not. So we're going to choose water as the one that has more intermolecular forces, so it is less ideal. Now in this instance, I have limited each pair has one that has hydrogen bonding and one that does not. So we can say that ammonia with its hydrogen bonding and water with its hydrogen bonding are going to be less ideal, more real, than methane or hydrogen. In other words, the ammonia molecules are much more likely to be interacting with each other than the methane molecules. They're going to act very ideal. The methane molecules in a gas are going to completely ignore each other. Hydrogen gas, those molecules are probably going to completely ignore each other, where water molecules are more likely to have interactions so that several water molecules could be clumped together. And so that summarizes our correction for intermolecular forces. So we basically have two ways that we can deviate from an ideal gas and create a real gas. When molecules are very large, or when molecules have strong intermolecular forces. That large size, large volume, is a bigger impact under very high pressures or very small containers. And the intermolecular forces have a bigger impact at very low temperatures when they're not moving very quickly, or under very high concentrations when there's a lot of them to run into each other. So the question is, why do we even bother with the ideal gas law if we have to use and correct for the fact that these are real gases? So let's take a look at this last picture. This graph shows PV over RT versus pressure. And for an ideal gas, PV over RT should be 1. We can see that ideal gases, non-ideal gases have some strange behaviors. So for water, goes down and back up. Helium, straight up. Under very high pressure, less ideal. Xenon has a weird curve. Neon is pretty linear. We are not going to deal with why all those occur. But what I want you to see in this graph is where I marked we live here. So while there are some very real deviations from ideal gas behavior and real gases in industry under high pressures, we need to account for those behaviors. In our everyday lives, pressure is so low at 1 atmosphere that we can pretty much ignore it, and the ideal gas law works with us almost all of the time. So it's really good to know that even though real gases are real and they can have a really big impact on gas behavior, for our everyday calculations, we don't need to worry about it.